Well, hello, everybody, and welcome. My name is Jackie. I'm the manager of planetarium programs at the California Academy of Sciences, and I'm very excited for you to be all joining us for our tour of the universe today. This is our monthly live stream where we take a tour of our universe starting relatively close to home and all the way out to the visible universe, and I promise we will bring you back home. Now, this is completely live, 100%, and I will be piloting our software, which is called OpenSpace. It's an open source planetarium software that you can actually download on your own home computer. And everything we're about to see today is based off of real data. So we are actually looking at where the International Space Station is right now. And we can zoom on out just a little bit. I believe right now it's actually over the Pacific Ocean. We'll take a closer look when we get a chance. But we are actually going to start our tour at the International Space Station, which is the farthest humans travel nowadays. Now, you can fit about 6 astronauts on it at any one time, and it is the largest object that we have built in space. It's about the size of an American football field, or I like to say the Academy of Sciences. So if you have ever been in our building and walked from one side of the building to the other, you have actually walked the length of the International Space Station. Now, not all of it is being used by humans. In fact, we have our solar panels on the upper right and lower left. And where you see those cylinders in the center, that's where humans actually do reside. But we are actually going to get much further away from the International Space Station, or ISS for short. And when we do, I'm going to go ahead and bring up something that can help us track it, the path of it, in kind of this orangish color. Now, it may look like the International Space Station is actually plummeting towards Earth. That's not the case. We're just zooming out. And soon you'll actually see that we're going to zoom out far enough to see the Earth as a whole. Now, the ISS is as far as humans do physically travel nowadays, though there are plans in the works to change that. Some people want to go to Mars, and hopefully we go back to the moon. But in the meantime, our astronauts are traveling very quickly around Earth. It takes them about 90 minutes to orbit us just once. In fact, you can look for the ISS pass overhead in the nighttime sky, and you're just looking for something that looks kind of like a star, but moving very quickly. And you can look this up at any point. But let's go ahead and keep on zooming out. And we can see our planet Earth, and you may notice that we can see some of the clouds on Earth, and some places there's not clouds. As I mentioned earlier, this is all based off of real data. So these are NOAA satellites that are orbiting around our planet, and they happen to just miss that area that we don't see any clouds. So promise you there are probably clouds there. We just don't know what they look like right now. And I can see the North America towards the bottom of our Earth right now, which means I was right on the Pacific Ocean. I'm glad I know my geography. But let's go ahead and continue our journey. And let's go ahead and maybe meet and explore our closest natural neighbor. I've quickly brought up the path of that object in space, and that is the moon. Now, the moon is as far as humans have traveled out into space. The Apollo astronauts came out here in the 1960s, and it took them about 4 days to get to the moon. Now, even though the moon is our closest natural neighbor, doesn't mean that it's close in human terms. The moon is around a quarter million miles from our planet. And as we get further and further out today, we are going to go distances of millions, billions, and sometimes even trillions of miles. So when we get to these far distances, it actually doesn't make sense for us to talk about distances in meters or yards. I'm going to use a different yardstick, so to speak. The speed of light, the fastest thing that we know of. Now, if we were actually traveling the speed of light, which is almost 200,000 miles per second, it would take us 1.5 seconds to get to the moon. So we say that the moon is 1.5 light seconds away from our planet. But let's go ahead and zoom in just a little bit closer to look at the surface of the moon. Now, the moon gives an illusion that it's been hit by maybe asteroids or meteors more often than us. Well, Earth is actually a very big target, so we get our fair share of impacts. But there's something a little bit different about the moon. It has no atmosphere. So, because there's no atmosphere, there's no weathering, there's no erosion, and there's no plate tectonics that are moving around. And so, nothing is erased on the surface of the moon once it's created. So, once those craters appear, they don't disappear like they sometimes can here on Earth because of our erosion and atmosphere. But let's go ahead and zoom out just a little bit further so we can see the full path of the moon around Earth. And when we're looking at this, we can actually see it goes a fair bit of distance. It takes about a month for the moon to travel around our planet just once in its path. Or I like to call it a month because it's not a full month, it's 29 and a half days. But I'm going to go ahead and bring up the paths of some of the other planets in our solar system. So now you see a line coming out from Earth. If we zoom out just a little bit more, we can see the paths of the inner planets. We have Mercury closest to the Sun, then Venus, Earth, Mars. Then further out would be the path of Jupiter, Saturn. Coming into view is Uranus, and even further out is Neptune. Now, when we're this far out, I like to pause and talk a little bit about something you might notice of a sizable gap in between Mars and Jupiter. Now, there's not nothing there. It's just not showing you everything that we have in our solar system right now. But what's there is our asteroid belt. So I've brought up the paths of some of the asteroids in our asteroid belt, about 60% of them, because if I showed you every single one, my computer would actually crash. But I like to pause here for a moment because I like to talk about another object in our solar system that's in this area. And I'm bringing its path up. It's kind of a lighter blue color, kind of in the middle of the asteroid belt. I'm curious if anybody has any ideas of what that object might be. Well, if you are thinking Ceres, you are correct. Now, the reason why I like to talk about Ceres is because it's a great object to talk about when we're talking about how we think about our universe and how we label things. When we first discovered Ceres, we actually thought it was the only thing in between Mars and Jupiter. So we called it a planet, and it was pretty big. But then we found some other things and it realized, well, maybe it's not a planet. There's all these other small things around in the same area. Let's call it an asteroid. Let's call all of these things an asteroid. And you may notice that we have another object we kind of renamed and classified recently. It's another object way out in the outer parts of our solar system. And I'm bringing its path up in light blue as well. And that is Pluto. Now, when we first discovered Pluto, we thought there was nothing out here. But soon, as our telescopes got better, as we started sending out different satellites to observe the outer parts of our solar system, we realized actually there's quite a bit out here. And I'm going to go ahead and bring up some of those objects. Now, all of these objects are relatively small, but some are actually quite large. In fact, Aries is about a little bit bigger than Pluto itself. So instead of adding a bunch of more types of objects or calling them all trans-Neptunian objects or TNOs, a group of astronomers came together, the International Astronomical Union, and decided, okay, we need a better definition of what a planet is. So they came up with these three criteria. One, the object needs to orbit a star. Well, Pluto and Ceres do that, so check. Two, it needs to be large enough, massive enough to have its own gravity strong enough to pull itself into a round or spherical shape. Well, Ceres and Pluto are both round, so check. And three, it needs to have cleared its path, meaning there can't be anything in its orbit. Things can be orbiting around it, but not in its orbit. So Ceres goes right through the asteroid belt, and Pluto goes right through the Kuiper belt, or these trans-Neptunian objects. So they decided to make up a new category called dwarf planets. And actually, we now have quite a few dwarf planets that we know about in our solar system. So I like to just take a moment and talk through how everything we're seeing is based off of our own perspective, how we are categorizing and how we are seeing things. All right, I'm going to go ahead and turn off some of these objects because they tend to slow down my computer and we have quite a bit to go. But let's go ahead and recap how far we have actually gone. So it would take us 1.5 seconds to get to the moon at the speed of light. So we say that it's 1.5 light seconds away. The sun is 8.5 light minutes away. And if we were able to go from one side of Pluto's orbit all the way to the other at the speed of light, it would take us 10 hours. So it is 10 light hours across. But even out here, we can actually check in on our human influence. I'm going to go ahead and bring up the paths of some of the fastest and farthest spacecrafts. We have Voyager 1 and Voyager 2, Pioneer 10 and 11 that were sent out in the 1970s. And more recently, we have the New Horizons mission that went out to Pluto in 2015. Now, these are the fastest and farthest our spacecrafts have gone, and none of them have traveled as far as light travels in one day. But let's go ahead and continue our journey. We're now going to start going out to distances of light years. We'll start flying past some of the closest stars to us. Now, the closest star to us, well, beyond the sun, is about 4 light years away from us. And even way out here, we can actually check in on our human influence one last time. I've brought up a sphere that shows approximately how far our radio signature has gone out into space. Now, since radio is a type of light, it's always traveling the speed of light. And our first radio and television signals that could get out of our atmosphere were sent around the 1930s. So this is about 90 light years away from us in all directions. We can also check in on how many planets we have found outside of our solar system, what we call exoplanets. So every circle is around a star that has at least one confirmed exoplanet. And at the rate we are looking at, it seems like most stars have planets around them and multiple planets. Now, if you look carefully, we can actually see there's several planets inside that radiosphere. So who knows? Maybe there's somebody listening to Nat King Cole right now. That would be pretty cool. Okay, still have a little bit to go. Actually, a lot to go. Let's go ahead and continue our journey. And as we zoom on out, I want you to keep an eye on that radiosphere. See how long it takes for you to be able to see it. And as we zoom on out, we'll start to see the large-scale structure of our galaxy, the Milky Way. Now, we live in what we call a spiral galaxy. You have these beautiful spiral arms with a bunch of stars in the center. And it's a pretty flat disk as well, filled of gas and dust and stars. And we are about two-thirds from the center of the galaxy. And right at the center are a bright group of stars. And if we could get past those at the very, very center of our galaxy, well, you would see basically nothing because we have a supermassive black hole at the center of our galaxy. And that is about 4 million times the mass of our sun. All right. Do you still see our radiosphere? Go ahead and see if you can point towards it. It is right where my arrow is. Again, two-thirds out, kind of about 7 o'clock if we thought of our planet or our galaxy as a clock right now. That's our little corner of the galaxy. Now, if we are at distances of actually thousands of light years. In fact, from one side of our galaxy to the other is about 100,000 light years across. But our galaxy is actually just one of many galaxies out here. Now, our galaxy has about 400 billion stars in it, but every dot we see now is not a star, but its own galaxy with its hundreds of billions and sometimes even trillions of stars. And it may seem like somebody accidentally spilled some cosmic skittles in the universe. These aren't the actual colors of the galaxies. These actually show us the different surveys that mapped the galaxies. But let's go ahead and we are continuing our journey. And we're going to start to see the large scale structure of our universe. And I like to give us this view, again, because of our perspective. Now, it may look like our galaxy is, or our, sorry, our universe is shaped like a bow tie or a butterfly. This isn't the actual shape of our universe. We are making the map. So, if something blocks our view, say gas and dust from our own galaxy, we can't see beyond it, so we can't map it. And like I said earlier in our program, this is based off of real data. So, if we haven't mapped it, we're not going to show you. We're pretty sure there are galaxies out here, we just don't know where they are. And as our technology is getting better and better, we're starting to be able to see beyond our galaxy, but we haven't quite been able to make the full map yet. The other thing you might notice from our perspective is that it looks like we are the center of the universe. Now, as many people might think that they are, we are not. Again, it's our own perspective. We are the ones making the map. We are looking out around us. If we were to go to any one of these other galaxies, say in the upper right, or now upper right, or upper left, we might see it as we are the center of the universe and we were making the map. As far as we know, there's actually no center of the universe. All right, we do have just a little bit further to go, and we're going to start to see some of the early objects in our universe, what we call quasars. They're the bright cores of some of the first galaxies. And I do mean earliest because any time that we are looking out into space, we're kind of time traveling in a way. Because the light of those objects has to travel so far, by the time it actually travels all that distance and gets into our telescopes, we're actually seeing the light of those objects as they were in the past, not how they look today. So, for example, when we were talking about the closest stars to us, the 4 light years away from us, that's how they looked 4 years ago, not how they look today. And we are now seeing the universe as it was billions of years ago. And because of that, there's only so far we can go, only so much we can see in the universe. And that edge now of our universe is all around us. What we're seeing is the cosmic microwave background, or CMB. Now, if you had a radio telescope and could see in the microwave range of light, you would see this everywhere you looked. In fact, the first radio astronomers were pretty confused by this. They looked up at the sky with their telescopes and they're like, what is going on? Why are we seeing interference everywhere we look? But soon they realized it was actually something in space they were seeing. This is what the universe looked like a few thousand years after the Big Bang. So we can think of this as our baby picture of the universe, the first light we can see. But since this is the edge of our universe, that means we can't go any further. So we need to start heading back home. So now, if we were actually that far out in space and we were actually flying the speed of light, it would take us 13.7 billion years to get back home. But thankfully, we have the magic of our planetarium software. So it should only take us about a minute. But one more thing I want to point out as we zoom on back home, everything that we've seen so far today, all the stars, galaxies, the cosmic microwave background, that's not everything in our universe. There's dark energy, this mysterious force that seems to cause, or that's causing our universe to expand and accelerate as it's expanding. We have dark matter, some mysterious substance that doesn't seem to interact with light at all, but we see evidence of it in between and the edge of galaxies especially. And we call all these things dark matter and dark energy, well, because we're not quite sure exactly what they are, but we do know that they exist. So everything that we've seen is only 4% of our universe. The dark energy and dark matter make up 96% of our universe. And that may make us feel a little bit small, like we're one tiny dot in this homogeneous universe. But I like to think of it this way. Yes, we're one tiny dot, but look at all that we have found, almost entirely by looking through telescopes. And there's a whole lot more for us to discover and a whole lot more for us to learn. And that's what makes a wonderful time in human history, that we're not just able to learn about these things, but show them like this, the map of the cosmos in 3 dimensions. And we're finally starting to unravel the true nature of the universe. But we're only just starting to unravel it. The rest? Well, that's up to the next generation of scientists back here on planet Earth. As we're heading back home to the third rock from the sun, the only place in all of this that we have found life so far, and that's pretty incredible to think about. And we are back home. And I want to say thank you, everybody, for joining us for our tour of the universe. And I hope you have a wonderful rest of your day. If you would like to learn more about our planetarium software called OpenSpace, the open source planetarium software, you can go ahead and click on the links that will be in our chat. Also, if you like this program and want to see more, we would greatly appreciate you filling out a survey. Otherwise, I want to say thank you, everybody, for joining me, and good night.